my computer had a total meltdown, and I had to restart the recording after like being interrupted. Right? Anyway, I was talking about this purple level curve here, and then I said, "What happens if I were to spin this thing?" So here we are in GeoGebra. Imagine drawing that level curve right there, and then turning this whole thing and watching the level curve move as we spin it, right? Or as we turn it. And we get down to right there, right there. Okay, here's the unit circle. That's my constraint. What would be true looking straight down, having the contours in front of us? I hope you see that they would have to be parallel, because if or they would have to be tangent to each other right there. It would skim just like that. This should be an ellipse, you know, my drawing skills, whatever. But look, it would skim. It would be tangent. They would not cross each other. So if I come up to here, where would that, which one of these level curves that we see is the one that's going to maximize it? Well, see, can you see it? Can you see it? Boom, it's that one right there. Hopefully you see that. Hopefully that makes sense. And then think about which one is going to be this low one. Well, that's the one where it's tangent, but we're on the lower parts of the level curves. Remember, this was 0, and they get bigger as we go out. So let me draw that one in. Boom, there it is right there. We got it in pink. This pink one right here and that one right there. What I want you to see is that that spot right there, if you look at the red line right here that, remember, is the unit circle, that's where those two are parallel. So, or where they're tangent. So, I'll write that down below. So, the level curves for f of xy, in this case, it's f of xy equals x squared plus 2y squared. All of the little blue circles must be tangent to g of xy equals c. G of xy equals c is that x squared plus y squared equals 1. And this takes us back all the way up to the top, right here. Remember? Where is it? We have right here. The gradient for a function is perpendicular to the gradient, or sorry, to its level curves. And the same thing is true for that g of xy, right? Remember, I could make that same argument because it has the exact same form. So what does that mean? Well, the pink gradient might look like that. And the purple gradient, or sorry, and the red gradient for, and by the red gradient, I mean the gradient for g of xy equals x squared plus y squared, which would be that one, might look like this, right? Or it might look like that, right? It doesn't matter. What matters is that they are parallel to each other. So what does that mean? Let's go all the way up to the top of this mess. If two vectors are parallel, then they are constant multipliers of each other. I can find a constant such that I can multiply it by 1 to get the other. So these arrows down here are the gradient. That means del, well, that means del f is equal to del g with some constant multiplier out front. What do we let that multiplier be? Lambda. And what does that do? It sets up my equation. F sub x equals lambda times g sub x, and f sub y equals lambda times g sub y. And then when I'm doing this, I got 3 variables, right? So what is my last equation? Because I only have 2 equations and 3 variables, and in order to solve that, I need to have 3 equations. Well, we pull this guy in, which in the general form is this right here. So I pull in g of x comma y equals my constant. That right there becomes my system of equations that finds the spots that I'm looking for right here. And that is why Lagrange multipliers work. I would love to just like drop the mic and leave that there, but I do think that this would be incomplete if I didn't actually solve the problem that we spent so much time talking about. And it actually has like kind of a weird spot to it. So let me come down here. I've done the solution out. Del f equals lambda del g. The gradient for f is 2x and 4y. That's the partials of this. The gradient for g equals x squared plus y squared. Well, that is 2x and 2y. So I'm going to put those lambdas here. You might say, all right, I'm going to divide by 2. So divide by 2x and get lambda equals 1. And then you divide by 2y here, and you get lambda equals 2. And then you're like, oh my god, this is unsolvable. But then you say to yourself, oh, I see how to solve this thing. This upper equation, if I make x equal to 0, or if I make y equal to 0, it satisfies this equation. So if I make x equal to 0 or y equal to 0 independently, I get these two solution sets over here. X equal to 0, plug in here, y squared, y is plus or minus 1, right? And then over here, y equal to 0 plugged into the constraint, I get x equals plus or minus 1. Then I come over here and I plug those values in. So I just did them together because these x values are going to get squared, so the negatives don't matter. So f of plus or minus 1 gives me, f of plus or minus 1 comma 0 gives me 1 squared plus 0, which is 1. F of 0 comma plus or minus 1 gives me 0 squared plus 2 times 1, which is 2. So that means that this is the min and this is the max. And now we need to see, does it fit? Does GeoGebra agree with us? So let's go over there and look. All right, you can see now I've got the positive x's there and the positive y's there in my right-hand system, so it's spun normally. Now, I've got A, 1, 0, 1. That would have been the min. And B at 0, 1, 2, right? So let's see. Hey, there it is. It's the low point. Yay. All right, let's check the other one. Here it comes. Drum roll. Okay. Bam! Found it. Sick. Anyway, I really do hope that all of this work helps you see why the Lagrange multiplier process works, at least with a two-variable system and a single constraint. You can get more complicated in other ways, but I hope this helps you see why it works. And I also am sorry that I had audio issues and had my computer catch on fire in the middle of video number 2. But anyway, thank you, and yeah, hope this helps.